This is going to be a short, hopefully, video about the concept that can lead to baffling in the minds of many students. The concept of, if I can get my pen, the concept of the mole. Okay. The mole. The mole, what's it do? Well, first of all, there's a problem. The mole is the solution to a problem, but we can't look at the solution until we know what the problem is. A problem exists in chemistry, how to count atoms. Why is that a problem? It's a problem because we can't see them. Because they're too small. How'd you count them? That's the problem. So the solution is the mole. Okay, so we still don't know what the mole is, but we know it's a solution to a problem. All right, and that's more than we knew a few minutes ago. Okay. So if one atom is too small to count, then let one become, this is one, not I. I'd hate to think that was I. Let one become a very large number. So we're going to say that 1 has now become 6.022 by 10 to the 23rd power. That's our new 1. We call it Avogadro's number. It has the symbol capital N, lower script capital A, frequently. Later on in another video, I'll show you where this number comes from. It's not just a random number. It's actually the ratio of two fundamental constants, but it's conveniently large enough that we can see it. So you might not be able to see one atom, but you can definitely see Avogadro's number of atoms and manipulate them with your huge hands, which essentially is what we need to do to count, right? You count with your hands. Okay, so we've got a new definition. So we said that let 1 become a large number. So we know that 1 mole of X by definition is Avogadro's number of X. So we just made 1, we've replaced 1 with Avogadro's number, and we remind ourselves we've done that by writing the word mole. So 1 mole, let's make this look like a 1. 1 mole of something is Avogadro's number. 1 mole of potato chips is Avogadro's number of potato chips, etc. That would be a lot of potato chips. Okay, so that's a definition. What else would I like to say about that? Let's see. Okay, so eventually we're going to have to pivot into chemistry. Oh, first of all, that's what I was going to say. Mole, if you wonder where mole comes from, it comes from the word molecule. Right? That's where mole is coming from. But there's a caution. Don't confuse moles with number of molecules. They're different. by a factor of Avogadro's number, as we said initially, because they differ by a huge amount, which is Avogadro's number. But that's where mole is coming from. It's coming from a specific number of molecules. Okay, so let's pivot into something chemistry-ish. So first of all, a definition. So by definition, if we take the isotope carbon-12, take the isotope 12 carbon, then (12 grams of carbon-12 is exactly 1 mole of carbon-12, which is exactly Avogadro's number carbon-12 atoms. Okay, so this is, everything is based off of carbon-12 in 2020. It hasn't always been that case, but it's definitely that case now. So let's take, so that's our definition. We can take carbon the way you see it in the periodic table. So it's an abundance mixture of isotopes. So we know that 12.01 grams of 12.01 carbon-12 is 1 mole of 12.01 carbon, which is Avogadro's number of 12.01 carbons, right? Goes without saying. If we look at hydrogen, so the periodic table I'm looking at gives it to 3 decimals. If we look at 1.008 hydrogen, then 1.008 grams of 1.008 hydrogen is 1 mole of 1.008 hydrogen, which is Avogadro's number of 1.008 hydrogen. Okay, and we can do the same for any element in the periodic table. So in general, A grams of any, so A is the atomic mass, or the mass number if it's an isotope. A grams of AX, where X is the symbol of the element, is by definition 1 mole of X, which is Avogadro's number of X. You can do that for any element in the periodic table which has all the varieties of A. Okay. What about molecules? So take, for example, water. Well, water is a mixture of, let's say, 1.008 H, 1.008 H, and 16 O, right? We've got 2 H's and an O. Okay, so I know that the formula weight is, I'll just grab my calculator out real quick, 1.008 twice plus 16. Okay, so if I add these numbers together, then the formula weight of water, actually we're just going to round to 2 decimals. So 18.02 grams per mole, or you could say atomic mass unit. atomic mass unit means the same thing as gram per mole. So therefore, if what we did for a single element, now we have a collection of elements, we just add them together. So I know that 18.02 grams of 18.02 water is 1 mole of 18.02 water, which is Avogadro's number of 18.02 water. Okay, so you typically wouldn't write it like that with the 18.02, but this is just a a teaching environment, just to let you know where these numbers are coming from. Okay, you could do the same for CO2. So CO2, we've got carbon plus 2 oxygens. So just doing a bit of math in my head, we've got 44.01 grams of 44.01 carbon dioxide. Well, that's just 1 mole of 44.01 CO2, which is Avogadro's number of 44.01 CO2, etc. You can do that for any compound. Okay, what if we had an equation? Let's say we have a balanced equation. So you'd have to look at my other videos on balancing equations. So let's say we have, I don't know, NaNO3 plus AgCl to give NaCl plus AgNO3. I'm not worried about solubility of solid, liquid, or a gas. I'm not really bothered here. But let's say we had this balanced equation, and it's balanced at the moment. There's an equal number of the same type of element on reactant and product sides. What do we know? We'll look at the ratio. We can have a mole ratio, and that's these coefficients here. So any coefficient that precedes the chemical, that would be the mole ratio. And I can see, you typically don't write 1, but we can see the absence of a number means that the number must be 1. So this is in a 1 to 1 to 1 to 1 mole ratio, right? Okay, what does that mean? Because ultimately we're going to have to start doing calculations at some point in chemistry, right? That means that mole ratio, once you know it, that means that 1 mole of NaOH, sorry, there's no NaOH, where am I thinking? 1 mole, so the 1 here is the 1. 1 mole of NaNO3 is equal to 1 mole of AgCl is equal to 1 mole of NaCl is equal to 1 mole of AgNO3. That's what it means. That's what it means, and that's what we'd need when we want to do calculations. So for example, let's say the question said, how many moles of AgCl, sorry, let me just see what I wrote. I've just spotted, it won't matter because I'm not really paying much attention to the chemistry of what I'm writing, but I've just noticed what I wrote doesn't make any sense. So only a true chemist at heart would have spotted that. But let's correct it real quick. 1 mole of NaCl. Okay, a chemist would spot that, and I'd never hear the end of it, so for purposes of karma, if nothing else, let's fix it. We'll all feel better about ourselves when we do. Okay, so it takes but a moment. So NaCl, AgNO3, NaNO3, AgCl. All right, that was close. All right, so let's get back. I spotted it as soon as I started writing AgCl. All right, how many moles of AgCl are produced from 3 moles of NaCl? So that's our question. Let's do our answer in red. So we're going to use dimensional analysis. I have other videos on dimensional analysis. This is a quick intro video on the mole. Okay, so I know I need to return, let's see, moles of AgCl. So I can write mole of AgCl. And what do I know? Well, I know from this mole ratio that I have 1 mole of AgCl, and I need to set that equal to something. Well, I know it's equal to 1 mole of NaCl. All right. So I can write mole of NaCl here. And now I can use my input 3, which is my input. So it's 3 multiplied by 1 divided by 1, which is 3. So I can start to do real chemistry calculations as soon as I introduce this concept of the mole. And I can start to I can start to do real chemistry calculations. So this is just a taste of what we need the mole to do for us. I'm not going to go into stoichiometric calculations here. That's definitely another video. But let's just recap on what we did do. We introduced the concept of the mole as the solution to a problem. The problem was, how do chemists count atoms when they're too small to manipulate with our hands and we can't see them? The solution is the mole. Ta-da! The mole essentially is a scaling factor. It's not a random scaling factor. It's convenient that it's large enough, but it's definitely a ratio of 2 constants in the universe, which we'll see in another video. So it's a real amount. It's not made up by people. We have definitions. Mole of X is Avogadro's number of X. The word mole comes from the word molecule, but don't confuse them, they differ by a factor. We have a definition, and we saw what we can do with it, both for elements and for molecules. And finally, we saw how it leads into setting the stage for stoichiometric calculations. And that will wrap up this video.